Okay, so in this video, I'm going to be talking about position, velocity, and acceleration, and basically how they're all related to each other. And how they're related to each other are just through integrals and derivatives. But basically, I've written that down already on the left side of the screen for you. So if you want to just take a look at that real quick, go ahead. But before I begin, I just want to talk about one thing. So if you're taking physics without calc this semester, don't be too alarmed in these videos if you see a lot of calc. The way that I think about it is that physics can definitely not be taught without math. That's just obvious. There's too many numbers involved. But I also see it as that physics can't be taught without calc either. I'd rather show you all the material possible and rather not hide things from you, because I feel confident in everyone. Everyone could be able to do calc. It's just if they have a really good professor or they try really hard. It's almost one or the other with that. Or they're just, I guess, naturally super talented, or I don't know. But I have faith in you is what I'm saying. So if you're taking physics without calc this semester, don't be too alarmed. Um, I'll try and say as many things without integrals and derivatives, but if I find it necessary, then I find it necessary. So just bear with me then. So in the end, basically, once you take the derivative of position, you're going to get velocity. So that's basically what that means right there. And then again, if you take the derivative of that, then you're going to get acceleration. So I'm going to write a little d right here. So derivative. So as you can see, if you do two derivatives, you're going to get of position, you're going to get acceleration. So that's what that really means is. That's the second derivative of position. So now if you go the other way with doing antiderivatives, or in other words, integrals, if you integrate acceleration with respect to time, all this is with respect to time. So if you integrate acceleration with respect to time, you're going to get velocity in the end. And if you integrate velocity with respect to time, you're going to get position. So write some eyes right there. So yeah, as you can see, if you do two, basically a double integral, you're going to get position. So double integrals, they look really scary, but this is probably the least scariest one because it's dt. If it was dt dx, start freaking out. But it's the same variable. It's the same variable in the end. So basically, I have an example of basically a velocity versus time graph here. And so v1 is going to be this portion right here. So this is v1, and it's just that's what this function is. And then v2 is right here. That's what this line is. And then v3 is just -1. So this is v3. So when you're taking the derivative, it's basically just the slope of a line, or is the slope of the tangent line of the graph is really what the true definition is. And the tangent line of a line is literally just that line. So it's literally just the slope of these lines in the end. So to start off, we're gonna start with acceleration, mainly because derivatives are just naturally easier than integrals. They just are. So really, we just have to differentiate these. And I'll go over the different basically the different types of differentiating in the next video. Real quick. I'm not gonna be too crazy with it. So we're gonna basically focus on acceleration right now. And so what is the slope of this line? Well, the slope of this line is literally just 1, because you go over 1 and you go up 1. And literally when you take the derivative of this, it's going to be 1. So a1 of t is just going to equal 1. And that's just because of the power rule. So I'm actually going to go over the power rule real quick. So if you have x to the n, if you differentiate that, that's going to be n, x to the n minus 1. And if it's just a constant, then like one, but basically for this scenario, it's going to be x to the 1 minus 1, So that gives you x to the 0. X to the 0 is just 1. Anything to the 0 is 1. So that's why the power of 1 came out in front, and then you basically have like times t to the 0 right here, which in the end is just 1. So you can ignore it, really, this part. But like that's basically how the power rule works for like t to the 1. So I'm going to undo all that real quick. But yeah, and then if you want to do the integral, I'll show that real quick for the power rule. It's going to be x to the n plus 1 over n plus 1. So differentiate this, you'll get this guy in the end. So this number comes out. So just because when you take the derivative, that guy comes out basically in front, in the minus 1. So so n plus 1 comes out. N plus 1 over n plus 1 is just 1, and then you subtract 1 to the exponent, like you do right here, and then you're going to end up with just x to the n. So you end up right where you started. So you take the antiderivative, take the derivative, you're back to where you started. So yeah, so that's basically a little brief thing about the power rule. So now a2 t is then going to equal, so if we take the derivative of this, the derivative of a constant is just going to be 0. Basically if you have t to the 0, yeah, it's going to be to the negative 1, but like n is 0. So if n is 0, it's going to be 0 times by like some function of t, which is just 0 in the end. So any constant, I guess you could write t to the 0 like this, but the 0 comes out and basically makes it as basically any constant is when you take the derivative is going to be 0. So so yes, when you take the derivative of this, you almost do it in pieces. You do this part and this part. So you ignore the addition sign and you just do them one at a time. So this is going to be negative 1 in the end for that one. And then when you take the derivative of this guy, that's going to be a3 of t, and then you're just going to get 0 in the end, just as that same rule. If it's t to the 0 comes out. So anyways, so if we graph that right now, I understand this doesn't go to 12, but we'll just imagine it does. So so really, I guess this is a terrible graph for us, but it's going to be 1 goes all the way. 1 goes all the way to 4, and then it drops down to negative 1 immediately. So yeah, as you can see, like if you try to get a tangent line right here, you can't really get a tangent line. Nothing's truly tangent to it. So it's not differential right there, and that's why there's like a vertical line right here. So so anyways, so we're going down to negative 1, and we go from negative 1 all the way to 9 then. And then after 9, we're going to go back to 0. So we go to 0 all the way until we're at 12. So yeah, so really that's your acceleration graph. I understand it's kind of small, but it's I didn't count for these numbers being small. Now that we have the acceleration graph, we're going to do the position graph. So we already have the velocity graph done, of course. So so we just want all 3 in the end. So typically that's the case. You could go higher than acceleration with your derivatives. You can go to a jerk, or there's even, I remember talking to one of my friends that I worked with about, and it went higher. I don't know. There's a crazy list that you can look up. A crazy list. But anyways, so we have s of t and we have t right here. So now we just need to integrate these. So in order to integrate, we can either get the area, or we can just integrate these using the power rule. Either way is the same, basically. One's more technical because it's integration, the other one, either way works. Either way works. So some functions you can't just see, oh, well, that's the area. These are triangles in the end, so it's super easy. So so in the end, we're going to integrate t right here. So S1 of t is then going to equal, so if you integrate that, you're going to basically get t squared, and then you're going to have a 2 in the denominator, so it's going to be times by a half then, really, in the end. And then we're going to have basically plus S naught. So we're going to assume S naught is just equal to 0. So you kind of need this to start out, because you kind of need an initial condition, because when you integrate you get plus C, and that's just a general integral. That's not really very specific. So we want to be a little bit more specific in physics is all. So so really that's going to be plus S naught, which is just 0 in the end. So, and you can see that to be the case because S naught is basically when t equals 0. So really this is just like S of 0 also, you know, same thing. So if this is 0 equals 0 squared, well then this has to be 0. So yeah. So now we basically need to figure out what the position is at 4 though. So we can't go on to this one and just integrate it and be like, yeah, that's the integral, just because we're going to be at a certain position. So if we figure out what S1 of 4 is then real quick, so plug in 4 in here, we get 16. 16 divided by 2 is 8. So we got 8 in the end. So really we're going to be starting at 8. So if you imagine this is, you know, just like this is your s-axis. So if you don't have to worry about t at all, we basically went all the way to 8 for v1, but we can't start somewhere else. You know, we have to start back here. You know, you're not magically at like some time gonna jump from 8 to -6. That's not a thing. So you have to take S1 of 4 equal to 8 and just set this actually equal to S2 of 4. So just so it's continuous. So this graph is continuous, and you basically want basically this is the derivative of it. So your position graph in the end is going to be continuous and differential, just because you don't pick up your line, pick up your pen when like basically creating this line. There's no gaps, no junctures basically. So so in the end, here let me get rid of the dots. Yeah, so I'll rewrite that here too. So S2 of 4, you know, so it has to be consistent. It has to be consistent. So anyway, so if we integrate v2, then we're going to get -1/2 t squared, you know, so same thing, plus 1 to the numerator, and then divided by basically 1 plus 1, which is 2. So, and then you keep the constant out front, which is negative, -1. So and then when you integrate 8, you're going to get, so it's basically t to the 0, so plus 1 to that, you're going to get 8t. And then now it's going to be, you know, just basically plus c at this point. So so now we have to plug in 8 into here, and then plug 4s in for our t's, just to figure out what c, well, let's say c2. What C2 is. Technically this was like C1, you know, so so anyways, so we have 8 equals -1/2 4 squared, so that's just really 16. So 16 plus 8 times by 4 plus C2. So so really this is going to be just -8. So C2 in the end is really 8. So since this is -8, when you add it to the other side, it's going to be +8. So, and then this is negative 32 when you add, this is 32. When we subtract it to the other side, it's going to be negative 32, which should just equal negative 16 in the end. So, so yeah, so this guy's negative 16. Okay, so sorry about that. Go back and just delete some stuff so I can have more space. So yeah, I just deleted the integral definitions of S and V, but I still left the power rule for us. So we have S1 completed, we have S2 completed now. So so really we just have to continue on what we're doing right here, you know. So S2 now, but instead of 4, we're focused on the red line right here. Instead, this juncture, which is 9. So 9. So we need to do S2 of 9. And plugging a 9 in here, we get negative a half. And then it's going to be 81 plus 8 times by 9 minus 16. So we're going to pull up our calculator real quick. So negative 0.5 times by 81 plus, just put in 72, that's what 8 times 9 is, minus 16. So we get 15.5. So so this is 15.5. That's equal to S3 of 9. So write that on the other side. So equal to S3 of 9. So so anyways, and all these are going to be in meters in the end. So if this is meters per second squared, this is going to be in meters then. So seconds. Okay, so all the units are right. So so in the end, now we have to merge them. We have to merge S3 and S2, just because this is a, like I said, a continuous graph. So anyway, so when we integrate this guy for S3, we're going to get negative t then plus C3. So when we plug in basically 9 into here and 15.5, we're going to get 15.5 equals 9, well, negative 9 plus C3. So C3 is then going to equal, so add 9 to this side. So that should be 24.5 in the end.